3.4 is related rates, which is a type of application problem that you use calculus to solve. So that's our goal, right? Is by the end of this lesson, we're hoping we can use related rates, or I can solve problems that involve related rates. So when we go to find our related rate story problems or application problems, the idea is that we're going to find a rate of change with respect to time of one quantity by using the rate of change of a related quantity. That's why they call them related rates. Here's the steps we're going to follow to do these. And like always, these steps will make more sense when we actually apply them and go through a problem. So we'll keep referring back to these. All right, so step number one is if there's not a figure, like sometimes they already have it drawn for you, but if not, you want to draw a figure if necessary. There's some problems maybe that don't, that's not necessary for, but on a lot of these they involve some geometry figures, and drawing a figure has help. And then you can also choose variables for all the unknowns. You want to write what is given and what is to be found using your own variables and dt symbols. This is going to be different for us. Up until now, when we took the derivative of x, we always, it was dx, it came out to be 1. Now when we take the derivative of any variable, including x, when I take the derivative, I'm taking the derivative with respect to time. So when I take the derivative of x, I'm going to end up with a dx dt. So when you take the derivative of any of the variables, because we're taking it with respect to time, you always have to have that d dt each and every time. And that represents the change. In that case, it'd be the change in x. What is the rate of change of x? Step number 3 is to write an equation relating the variables. This usually is the hardest step, is coming up with that equation. A couple of really important things. If a quantity is changing in the context of the problem, it must be represented with a variable. If a quantity is constant throughout the context of the problem, then you're going to plug a number, a constant in there. And then C, it says look for a secondary relationship between quantities to reduce the number of variables. Sometimes you'll have to use a formula that involves maybe 3 variables. So if you can find a secondary relationship that we can do some substitution to narrow down just to 2, that can be helpful for you. Hey, once you've got that equation, number 4 is to use implicit differentiation. And then step number 5 is you plug in what you know to solve for what you're trying to find. Okay, so let's go through an example so you can kind of see these steps in action. The first, before I do that, they have a list of formulas here. These are all just geometric formulas you've all seen before, right? Pythagorean theorem, that's the area of a triangle, area of a circle, circumference, volume of a sphere, surface area. A cube, that E represents the length of one of the edges. It's kind of weird they use E. A lot of times you'll see that written with an S, the side length. Right? Take the side length and cube it. 6 times the side length squared. Volume of a cone, 1/3 pi r squared h. Area of a rectangle, perimeter of a rectangle. So those are all ones you're familiar with, but they're listed there because we're going to use some of those throughout this lesson. Okay, so this example number 1, the first 3 steps are already done for us. We didn't need to draw a picture, but they do have an equation that ties the variables together. This is our equation. X times y equals 12. That ties x and y together. It wants me to find the rate of change of y, dy dt. It tells me the rate of change of x, dx dt. It's equal to -6, and it tells me y equals 4. Okay, so we're going to do step 4 and 5. So step 4 is to do implicit differentiation. So here's my formula. Let's do implicit differentiation. So I take the first, which is x, times the derivative of the second. Well, the derivative of y with respect to t is dy dt. On these problems, I do not want you to put a y primed. Y primed usually is used to denote dy dx. We're doing dy dt. I want you to write down the dy dt. Okay, so I took the first times the derivative of the second, plus the second, which is y, times the derivative of the first. And be careful with this. The derivative of x, if it's with respect to x, is 1. But with respect to t, I have to do a dx dt. Equals the derivative of 12, which is 0. So there's step number 4. I took the derivative. Now we're going to plug in what we know and try to find what it's asking for. It's asking for this. I think it's helpful to circle it. That's what I'm trying to find it. Plug in what I know. I know y is 4, and I know dx dt is -6. I don't know what x is, but I can figure it out. If I go back up to this equation, if I know y is 4, I can plug 4 in for y and solve for x. X would have to be 3. Okay, now I've got everything but dy dt. I can solve this. So this is a minus 24. I can add it over. 3 dy dt equals 24, divide by 3. So dy dt is equal to 8. Now, normally there'll be a label on these, and most problems are going to be application problems or story problems, and they'll have some kind of context. This one, it doesn't tell us, though, so we're just going to leave it just like that. Okay, let's do one that actually includes, on this next problem, this number 2, you're going to be doing all the steps but number 1. Step number 1 is to draw a picture and to label the sides. On this one, that's already done for us, right? They have this triangle drawn with some stuff labeled. But let's read the problem. It says a windlass is used to tow a boat to a dock. The rope is attached to a boat at a point 15 feet below the windlass. So here's my windlass up here, and then there's a dock down there, and this side is 15. The windlass pulls the rope at a rate of 30 feet per minute, excuse me. So if you think about that, here's my rope along this side right here. It's pulling the rope. That 30 feet per minute is telling me how fast z is changing by, right? How fast the rope is coming in. Something to be really careful with. So let's put down dz dt. dz dt means the change in z with respect to the change in time. So it's in other words, it's the rate of change of z. When I put that down, you have to decide if it's positive or negative. If you look at z, that side length, as it's pulled in, that rope, the length of the rope is getting smaller, so z is getting smaller. That means that 30 feet per minute is actually a negative 30 feet per minute, because the length of that side is decreasing, z is getting smaller. So I know dz dt. When we continue on, it says, at what rate is the boat approaching the dock? So the question is asking the rate the boat is approaching the dock. So that means how fast is x changing by? So put that down. I'm trying to find out how fast x is changing by, or I'm trying to find dx dt. And the moment in time when we're trying to find that is when there's 25 feet of rope out. So that's when z equals 25. If z equals 25 up here, we can actually find out what x is at that moment in time too. Sometimes I've seen one time when a book called it the magical moment, this one moment in time when z is 25. So you can use Pythagorean theorem, right? 15 squared, supposed to be a 15, sorry. Let me try that again. So it'd be 15 squared plus x squared equals 25 squared. And you solve that, pretty sure x comes out to be 20. So I'm going to add that to my list up here of things I know. X equals 20. Okay, so I have my picture drawn. I have all the things I know. I know this. I know what z is at that moment. I know what x is at that moment. I know dz dt. I know dx dt. Step number 3 is to come up with an equation that ties really I know the rate of change of z. I'm trying to find the rate of change of x. So I want to tie those two together, that x and z. So one we can use is Pythagorean theorem. Before I plug anything in, this is really important. If you look under step number 3, it says you have to make sure that anything that changes is represented by a variable. So what it means by that is as the boat is pulled in, this side is going to change. This side is going to change too. So you have to represent them with variables, with x and z. This side over here is constant. 15 never changes as the boat's pulled in. So for that one, I can plug in a constant. So I'm going to use Pythagorean theorem. I'm going to go 15 squared plus x squared equals z squared. That's my equation that's going to tie those variables together. Okay, let's take the derivative. So the derivative of 15 squared would be 0. Derivative of x squared would be 2x dx dt. Derivative of z would be 2z dz dt. Okay, remember I'm trying to find dx dt. So now plug in what we know. I know x is 20, 2 times 20, dx dt. Equals 2 times 25 dz dt we have as negative 30. So we end up with 40 dx dt equals, we times all those together. I'm pretty sure that comes out to be negative 1500. You guys can check my arithmetic there. Divide by 40. So dx dt is equal to, and I'm pretty sure that comes out to be a negative 37.5. Hey, we want to label it. This was moving at, z was moving at a rate of, the measurement was feet per minute, so this will be the same. So x is changing by a rate of 37.5 feet per minute at that moment in time. At that moment in time when z is equal to 25, that's what it's changing by. Now it actually asks to write a sentence. On the AP test, they'll do this usually is you want to write a sentence answering the question. It doesn't have to be like a super long, complicated sentence. The question was, at what rate is the boat approaching the dock? So you would say the boat is approaching the dock at a rate of 37.5 feet per minute. That's a little bit tricky. I wouldn't say it's approaching the dock at a negative 37.5 feet per minute, because when you say it's approaching the dock, you already say it's getting closer to the dock. So I don't have to include the negative in my sentence. All right, let's try another one. So this is a policeman is traveling south toward an intersection. They spot a speeding car traveling east away from the intersection. When the policeman is 0.6 miles from the intersection and the car is 0.8 miles from the intersection, the policeman's radar shows that the distance between them is increasing at a rate of 20 miles per hour. If the speed of the policeman's car is 60 miles per hour, what is the speed of the car? Okay. Confusing, right? But let's draw a picture to help make sense of it. So you've got the, got the one police car up here. There's my police car. It's traveling south down to here. And then you have another car that's traveling east. So say it's going this direction over here. It's a very nice car. It's traveling that way. So let's travel in that direction. Okay, so let's label what we know. It says the policeman is 0.6 from the intersection. Now, first of all, before I do this, something to be careful of is as time goes by, the car is getting closer. So this side over here, this side is changing. So I need to represent a variable. So I'm going to call it x. But in that one magical moment where we're trying to solve this problem, we know the police car is 0.6 miles from the intersection. That's what x has to equal at that moment. This side is also changing, right? As time goes by, the car is getting further and further away. So this, we've got to put a variable too, because that side has to be changing. But at that magical moment, that moment in time that we're trying to solve for, we know that y is going to have to equal 0.8 miles. That's how far it is from the intersection. All right, let's see what other information it gives us here. It says if the speed of the police car is 60 miles per hour. Okay, so this is my police car up here. That's how fast x is changing by 60 miles per hour. So let's put that down. That's dx dt. It's the speed of how fast x is changing by. This is the really tricky part, is you have to look at x and decide, is x getting bigger or smaller? So if x is this distance right here, it's the distance on that side. If the police car is traveling that way, that means x is getting smaller. So instead of putting 60, I'm going to put a negative 60. And it wants to know the speed of the, oh, and it tells me one other thing. It says the distance between the two cars, which is this distance right here, it's changing. Let's label it. So that as the police car moves and that car moves, this side's going to change. So it has to be a variable also. So z equals, I don't know what it equals, but it does tell me that the speed between the two cars, right, his radar is picking that up. The speed between the two cars is increasing at a rate of 20 miles per hour. And that's going to be a positive 20 because it says it's increasing at a rate of 20 miles per hour. Okay, I think we have everything but z there, and we got to set up an equation. We can find z. If this side is 0.6, this side is 0.8, you can use Pythagorean theorem and solve that. It comes out to be, I believe it comes out to be 1. So solve for z. Z has to equal 1 in that moment. Okay, so now I've got my picture drawn here. I wrote down all the things I know. I'm trying to find, well, we never put what we're trying to find. The question is, how fast is this car traveling right here? So that would be the dy dt. That's what I'm trying to find right there. Okay, so now I've got to come up with an equation that ties them all together. Hey, well, this one works great. Again, we got a right triangle there. So this is another Pythagorean theorem problem. So I can go x squared plus y squared equals z squared. Now notice that all three are variables, and the reason why is because in the context of the problem is the two cars are moving, x is changing, has to be a variable. What this side is changing, it has to be a variable. So is the distance between the two cars. So you have to keep all three variables. On the last problem, that one side stayed the same, so we could plug the number in for it. Okay, let's take our derivative. So derivative of x squared would be 2x dx dt. Take the derivative of y squared would be 2y dy dt. Equals 2z dz dt. Okay, let's plug in everything that we know in there. By the way, I could divide it all by 2. In fact, I'm going to do that. I'm going to divide those 2's on both sides. So I'd end up with x dx dt plus y dy dt equals z dz dt. Okay, I'll start plugging numbers in. So I'm going to plug in. Let me slide this down a little bit. I'm going to come down here. I know x is 0.6. So I would have 0.6 times by dx dt. Dx dt I said was negative 60. Plus y. Y was 0.8 times by dy dt. See, dy dt was, oh, that's what we're trying to find. Let's just leave it alone. And that's equal to z, which is 1, times dz dt, which is 20. Okay, I need to solve that. I'm trying to find dy dt here. So times 6 by negative 60 would be negative 36, plus 0.8 dy dt equals 20. You could add the 36 over there. That would be 56. So we're going to end up with 0.8 dy dt equals 56, divide by 0.8. Okay, and so dy dt, that's how fast this guy is traveling. His rate of change there, and you divide that, I believe it comes out to be 70. So now we're going to, 70 miles per hour. So we're going to, again, write a sentence that answers the question. So I go back up there, it says, what is the speed of the car? So you would say, the car is moving away from the intersection at a speed of 70 miles per hour. That would be your sentence that you write down that would answer that. These are so much fun, right? We love it. Okay, let's try another one. This one's totally different. This one's no longer a Pythagorean theorem triangle or problem. We're going to have to use a different formula for this one. So it says gravel is falling on a conical pile at a rate of 10 cubic feet per minute. At all times, the radius of the cone is twice the height of the cone. That's going to be really important for us. We're going to use that in just a second. The radius of the cone is twice the height of the cone. So we'll come back to that. Find the rate of change of the height of the pile when the radius of the pile is 6 feet. And it tells us the volume equals, this is the formula for volume of a cone right there. All right, and write a sentence explaining the answer. So here's my formula. It gives us a formula on this one, right? Volume of a cone. Okay, let's go back though and figure out what's given to us. So if I look up here, it says gravel is falling on a conical pile at the rate of 10 cubic feet per minute. So that's really important. That's a rate of change. So is it the rate of change of the volume, of the radius, or of the height? Well, it's 10 cubic feet, and that's how fast it's falling on the pile. That's how much the volume is changing by. So let's put that down first. I know that dV dt equals 10 cubic feet per minute. It tells us down below that the radius of the pile is 6. So the radius is 6. We're trying to find out, the question is asked us is, find the rate of change of the height. So I'm trying to find dH dt. So that's my question mark right there. So if I come back up to this formula, notice how I have 3 variables. I have the volume, I have the radius squared, and I have the height. If you take the derivative as it is, something to be aware of is because those are times together, r squared times h, I'll have to do the product rule. Not only that, I'll end up with a dr dt. This problem does not tell us how fast the radius is changing. It doesn't tell us the rate of change of the radius. And so I won't know dr dt. So what I'm going to try to do is, if you notice, go back to your steps. When you're finding the equation, part C said, use secondary information to eliminate some of the variables. Okay, so we have less variables. Well, right up here it tells us the radius of the cone is twice the height. So off to the side, I know that the radius is equal to twice the height. What I can do then is I can do some substitution here in this formula. In place of r, I can put in 2h. So I have this formula now, v equals 1/3 pi times 2h squared times h. And don't take the derivative of that, I can simplify that formula. I'd have the volume equals 1/3 pi times 2h squared would be 4h squared times h would be 4h cubed. Well, what I've done now is, now I only have two variables. I have the volume and I have the height. And I'm trying to find dh dt, so I want the h in there. And I know dv dt, right? It's right up there. So I think we have everything we know. Now I can take the derivative. This is a little confusing, but remember this. Let's take the derivative. So the derivative of v would be dv dt. Over here, 1/3 times pi times 4. This whole thing right there, that's just timesing, all those times together is just a constant. So that's a scalar multiple. 1/3 times pi times 4, it's going to stay exactly the same. It's going to be 1/3 times pi times 4 times by, and now just take the derivative of h cubed. That would be 3h squared dh dt. So now I've got my formula there. Now I just have to plug all the stuff in there that I know and try to find my answer. So let's plug in what we know. Up above, I know dv dt is 10. So I have 10 equals, I'm going to simplify a little bit. 1/3 times 4 would be 4/3 pi times h. Well, the problem is I need to know h. It doesn't tell me h, but it tells me at the moment when the radius is 6. And right here we said the radius is equal to 2 times h. So I know 6 has to equal 2 times h. That means h has to equal 3. So I'm going to plug 3 in. So that would be 3 squared times by dh dt. Okay, I've got everything plugged in my formula. I just need to solve for that. So I'm going to, you could times by 3/4, right? Times by 3, that'd be 30 over 4 to get rid of that. 3 squared is 9, so I could divide by 9 over here. And I got pi, times by pi, so I could divide by pi over here. Over here on the other side, that should be it. I've got dh dt. I'm going to go back up here for, sorry. I'm going to go back up here for just a second. When I wrote this formula over here, I forgot that 3 right there. So let me go back. I apologize. Let's backtrack to right here and just fix this. So over here, if I wanted to, I've got that 1/3 and the 3. I can just multiply those together. So dv dt would equal 1/3 times 3 is 1. So they go away. So I end up with 4 pi h squared dh dt. Down to there. Okay, now I can plug in the numbers that I know. So I've got, I'm trying to find dv dt equals, I've got 4 pi, actually I'm sorry, I know dv dt. Well, I'm struggling here, guys, sorry, we'll get there. So I know dv dt, it's right up there, right? It's 10. So 10 equals 4 pi times, and in here I've got to plug in 3, the height is 3, right? Because, right, the radius equals 2 times the height, and the radius is 6, so the height has to equal 3. So 3 squared dh dt. We could simplify this side. I'd have 10 equals, I can do 4 times 3 squared. That's 4 times 9 is 36 pi. Divide by 36 pi. All right, so dHdt equals, dHdt is equal to 10 over 36 pi. I need a label there. So when I go to label that, think the volume up above, think of our units of measure. It was cubic feet per minute, right? In the original problem right up there, cubic feet per minute. So I go to do this problem. When I talk about height, it's not going to be cubic feet, right? Volume is cubic feet. Height is a linear measure, so it's just feet. So it'd be 10 over 30, 10 divided by 36 pi feet per minute. That would be my final measure that I come up with. Now we're going to write a sentence describing that answer. So my sentence would be as simple as, when the radius is 6 feet, the height of the pile is increasing at a rate of 10 over 36 pi feet per minute. Okay, and that would be your answer that comes there. As you can see, guys, there's lots of steps to these. They get tricky. You're going to have some questions as you go through and work down through these. Make sure you're contacting me. Ask me if you have questions, and I can hopefully help you get all those answered. These just take practice. The nice thing is usually if we practice enough, we usually get really good at these. And it actually ends up being, it's hard to believe right now, but these actually end up being some of the easier questions on the free response parts of the AP test. They usually put, not always, but usually they'll put one of these on there that you'll work down through. All right, thanks for listening again. Make sure you contact me with questions. Thanks, guys.